The fourth review video is going to focus on precision and accuracy. Here you see 4 dartboards representing what it looks like when you have low accuracy and low precision. Low accuracy and high precision, note that they're really close together. High accuracy, really close to the target but not very precise. They're kind of separate from one another. And then we see the goal, high accuracy and high precision. So accuracy, again, is just how close your value is, typically what we measure in an experiment, to a target value, the accepted value. This is calculated with percent error. It's a pretty common equation we use in first year. It is one you are going to use quite often, so I would add this to your formulas to learn. Accepted minus experimental over accepted times 100. Notice the absolute value sign, so it is always a positive value on the top. Really doesn't matter how you subtract the top. We're not concerned with whether you're too low or too high. We want to always make sure we compare that to the known value. Sometimes you'll see words like accepted, actual, theoretical. Those are all synonymous for the known value, the true value. Precision is how close they are to one another. We saw that with the darts. You can also refer to precision with the amount of decimal places you can get from a measurement. Obviously, the more information you can provide, the more precise your measurement's going to be. The closer your measurements are to one another, it's just a better indicator that your experimental data is valid, how it's being depicted. And we can examine precision kind of broadly by using range, or more precisely with deviation calculations. So here we are using the mass and the volume of water that was measured in lab 3 times, and we're going to calculate the density of it. You're given the experimental values that were calculated and what the true value of water is at 25 degrees, 0.998 grams per mil. So the first thing we're going to do is calculate an average. Average, we just sum up the 3 experimental values and divide by 3. However, that 3 is a exact value, so it does not have sig figs. It's a counted value. So when we look at our calculation, when we add these 3 together, we see that they all have 3 decimal places. So that's what we're going to report our answer to, since that when we add these together, we get I think it's like 1 point, or excuse me, 2 point, really close to 3. Sorry, but they have 3 decimal places at the end, and so that's what we want to report in our final answer when all is said and done. We also keep the units grams per milliliter because x plus x plus x would give me x. Our range would be the highest minus the lowest values. So we take the highest value, which is 0.990, and we subtract away from it the 0.955, and we get a difference of 0.035. Again, 3 decimal places because they both had 3 decimal places in the values that we were subtracting from one another. We do want to keep the same units, grams per milliliter. And finally, percent error, accepted minus experimental. Our accepted was the 0.998. Our experimental, we're going to use the average. That's what it tells us to do. And typically, if we have more than one measurement, we're going to always use our average value for our experimental data. And we divide that by the true value, the 0.998. Subtracting again, you may remember back to the first example with the significant figures. We want to keep the same number of decimal places. We want to combine this before we can divide. An order of operations, so we want 3 sig figs, or 3 decimal places more specifically, when we subtract. And then when we divide this, we're going to have 3 sig figs here. I believe when we subtract these 2 from one another, however, we get 0.025, so that has 2 sig figs, and that's why we have 2 sig figs in our answer. Percent error would also have times 100. I'm sorry, that got left out over here. And typically with any of the percentages, we're just going to round those to 1 decimal place. Sorry again about leaving out that times 100. This should help you to answer questions 15, A, B, and C. I will comment on A. It says, are the experimental densities precise? Why or why not? Are they close together, or are they pretty spread out? And you do have to kind of look at the numbers in the context of one another. I would look at what the range is broadly and see how the range compares to the difference between them. It looks like here we have 0.705 and 0.678. So we're dealing with a difference of probably around 0.027, which is a fair amount given the values that we have. I would expect for things to be more precise. They'd be all really close to one another. Here I told you about using the average experimental density for your percent error calculation. Round your answer to 0.1%. And typically, if your percent error is under 10%, you can say that your densities are accurate. Okay?